Welcome to this explainer. Today, we're tackling something that literally pushes the boundaries of human imagination. We are talking about the absolute giants of the cosmos, supermassive black holes. We're going to take a deep dive into just how massive these entities can actually get, how astronomers even go about weighing them, and what modern physics says about their absolute size limits. So, think about this for a second. How massive can a black hole actually get? I mean, you know that when a massive star collapses, it leaves behind a stellar mass black hole, maybe 10, 20 times heavier than our sun. But hiding out there in the centers of galaxies are these supermassive beasts that completely dwarf those numbers. So what's the ceiling? Where does physics actually draw the line?
Well, brace yourself because the theoretical ceiling is a staggering 1 trillion. Yeah, a trillion. According to recent models, this is the absolute upper bound for what astrophysicists actually call stupendously large black holes, or slabs. 1 trillion times the mass of our sun. It's a number so vast, it kind of breaks your brain just trying to picture it, right? But stick with me, because by the end of this explainer, we'll make sense of how the universe might actually allow these behemoths to exist.
All right, let's jump straight into section 1, supermassive black holes explained. Okay, let's get our baseline down. A supermassive black hole, or SMBH, operates on a totally different playing field than standard stellar remnants. We're talking anywhere from hundreds of thousands all the way up to tens of billions of solar masses. And solar masses is going to be our yardstick for this whole explainer. The leading theory right now is that an SMBH basically acts as the gravitational anchor right in the center of almost all massive galaxies. And what's really wild is that when galaxies merge, you can actually get binary systems. That's two supermassive black holes locked in this tightening, high-speed gravitational dance, eventually sending these immense gravitational waves rippling across spacetime. But we run into an observational hurdle pretty quickly, because while theory says they're everywhere, we only have unambiguous, clear-cut, dynamical evidence for a handful of them. Places like our Milky Way, Andromeda, M32, and NGC 4395. In those specific spots, we can physically see the velocities of stars and gas sharply spiking near the center, which is a dead giveaway for a massive, invisible point. But in most other galaxies, those star velocities are either flat or even dropping near the core. The gravitational noise of the galaxy itself essentially drowns out the black hole, making it incredibly tough to confirm they're there just by watching things move. So you might be wondering, if we can't actually track the stars in every galaxy, why are astronomers so confident these things are everywhere? Well, the answer is the M-sigma relation. Using the secure detections we do have, astronomers found this absolutely brilliant, incredibly tight correlation between the mass of the black hole and the velocity dispersion of the stars in the host galaxy's bulge. It's a remarkably consistent relationship, and what this tells us is that they co-evolve. It strongly suggests the formation of the galaxy and the growth of that central black hole are fundamentally linked, basically regulating each other through intense gravity and radiation over billions of years. Which brings us to section 2, the challenge of measurement. Now, measuring these things is where it gets really tricky. Our established detections rely heavily on that secure M-sigma relation we just talked about, but that's only pristine in about 10 nearby galaxies. When we peer further out into deep space, looking at active galactic nuclei and distant quasars, that method totally breaks down. Instead, astronomers have to rely on really complex and sometimes totally conflicting techniques. Take broad emission line reverberation mapping, for instance. This involves measuring the tiny time delays between light from the accretion disk and light from surrounding gas clouds to essentially weigh that central mass. The catch? These methods aren't universally calibrated yet, so you'll often see a mass calculated from reverberation mapping directly contradicting a Doppler measurement of the exact same object. It's frustrating, sure, but it also makes this a wildly thrilling, super active frontier of research. Moving right along to section 3, the theoretical size limits. So what actually stops a supermassive black hole from just eating the universe and growing forever? Well, physics actually enforces a cosmic speed limit. For your typical black hole, the absolute maximum mass sits right around 50 billion solar masses. And the reason why is fascinating. As they grow and consume matter, the intense radiation and star formation happening inside the accretion disk effectively blow the surrounding food source completely away. It literally starves the black hole and stalls its growth. And given that our universe is only 13.8 billion years old, typical black holes just haven't had the time to overcome that starvation phase. But there's a loophole. If a black hole has maximal prograde spin, meaning it's rotating as fast as physics allows in the exact same direction as its accretion disk, it becomes insanely efficient at feeding. That spin pushes the theoretical ceiling all the way up to a mind-bending 270 billion solar masses. Now for the really fun part, Section 4, the most massive titans. Okay, let's look at the absolute most massive entities ever discovered. Getting accurate numbers out at the edge of the universe is notoriously difficult, as we discussed, but these are our current heavyweights. Sitting right at the very top is Phoenix A, clocking in at an estimated staggering 100 billion solar masses. That number comes from a calorimetric model looking at the core regrowth of its host galaxy. Right on its heels is IC 1101 at 97.7 billion solar masses, which they calculated from the break radius of its central core. And then you've got TON 618 at 40.7 billion. Notice how these numbers are pushing right up against, and in Phoenix A's case, completely obliterating that typical 50 billion solar mass limit we just talked about, right? That heavily implies we're looking at extreme spin scenarios or some truly extraordinary violent merger histories. To really put this into perspective, let's bring that sheer scale back down to our cosmic neighborhood. Sagittarius A star, which is the supermassive black hole anchoring the center of our Milky Way, is roughly 4.3 million solar masses, which, don't get me wrong, is a monster in its own right. But compared to Phoenix A, wow! Phoenix A is over 23,000 times more massive than our galaxy's central black hole. If you magically dropped Phoenix A into the center of our solar system, it wouldn't just swallow the sun and the planets. Its event horizon would stretch so far out, it would reach deep into the Oort cloud. It's a scale of existence that just completely defies human intuition. But here's the kicker. That list of titans is far, far from complete. Just look at the data pouring in from the Sloan Digital Sky Survey. They've already detected over 200,000 quasars. These are the incredibly luminous, highly active feeding centers of distant galaxies. Any single one of those 200,000 deep space beacons could be masking a billion solar mass black hole right now. In fact, there are hundreds of black hole mass measurements currently sitting in the scientific literature that aren't even finalized yet, mostly because they're tangled up in those conflicting measurement methods we went over earlier. So our mapping of these cosmic heavyweights, it has literally just begun. Which leaves us with this final thought to chew on. How many more billion solar mass titans are hiding out there within those 200,000 known quasars? Are there actually stupendously large, trillion solar mass black holes lurking in the dark, just waiting to be confirmed? The universe is holding on to some profoundly massive secrets, and every single new astronomical survey brings us one step closer to dragging them into the light. Thanks so much for joining me for this explainer.